As with a lot of things, sometimes it's easier if we just use them in an example and we see how they're used. So let's do that with gravitational potential energy. We're going to find the escape speed from the Earth. What is the escape speed? It's the speed we would have to launch a projectile with so that it never returns to Earth. Normally, when we send rockets up and spacecraft, we don't just give them one big push and let go of them. They have a rocket on them with lots of fuel, and they push nice and gently, and they continue to push with their thrusters on the rocket. And as it goes up, it's always pushing with its rocket thrusters, and it goes nice and gently. But if we wanted to give something one big push, one velocity, and have it never return to Earth, what speed would we have to launch it from the surface of the Earth? And we'll ignore air resistance to calculate this. So if we take a look at our initial condition, we give our object some big initial velocity, and it leaves the Earth. And where does it end up? It comes to rest when it's infinitely far away from the Earth. Normally, we throw something up into the air. It starts to move away from the Earth. It comes to rest at some point, and then there's still a force of gravity acting on it, and it returns and it comes back and hits the Earth's surface again. In this case, we give it such a big speed, it leaves the Earth. The Earth is always pulling on it, slowing it down as it leaves. But by the time it finally comes to rest, they're so far apart that the force of gravity from the Earth is basically zero, and they stay separated. This is a typical energy lens problem. We'll find the initial energy and the final energy. Since we're ignoring air drag, the initial mechanical energy equals the final mechanical energy. Well, initially, what kind of energy is there? We have an object that's moving very, very fast, so it's going to have kinetic energy, and it's interacting with the Earth. And at the end, we could also have kinetic energy and gravitational potential energy. But we just said at the end, our object comes to rest, so this is going to be zero. Initially, it's moving. We have 1/2 mv squared. Where are we going to set our gravitational potential energy to be zero? Do we have a choice? No, we don't have a choice. The gravitational potential energy is zero when our two objects are infinitely far apart. And in this case, that's our final condition. So it goes to zero at the end of the problem. But it's not zero initially. At the surface of the Earth, it has gravitational potential energy. And don't forget, it has to be negative. And how far apart are our objects? The radius of the Earth. Our object is on the surface of the Earth, so they're a distance re apart. Remember, it's 1 over r, not 1 over r squared. So there's 3 things here to remember. Number 1, the object is moving so far away, we can't use our gravitational potential energy equals mgy. We have to use universal gravitational potential energy. Number 2, don't forget that minus sign. That's part of our formula. And number 3, we have so many 1 over r squareds in physics. Don't forget that this is not 1 over r squared. It's 1 over r. So just a couple of little things to remember when you use this equation. Now we can solve for v initial. We get 2 gme over the radius of the Earth. square root. And that's our escape speed. That's the velocity we would have to launch a projectile with for it to never return to the surface of the Earth.